Good afternoon again, everyone. My name's Andrew Halley, and I'm the Australian panel convener for CIGRE C4. The title of this presentation is Summary of Relevant CIGRE Activities Related to System Strength. You can see the 16 study committees listed there. They're grouped into four major categories. The A's represent equipment, the B's are related to technologies, the C's are related to systems, and the D's are materials and IT. Now, while I won't bother going through and discussing each one of the study committees separately, I think the headings give you a pretty good idea of what each one of those study committees actually does and what their focus area is. But what is worth mentioning is that many study committees are currently contributing to issues related to the increasing penetration of inverter-based resources and the various issues that the rollout of IBR is having on the operation and design of power systems going forward. So while I think everyone recognises that Australia is probably leading the way when it comes to IBR integration and the issues that come with that, it's worth remembering that other parts of the world are following in our footsteps, and some of them are not that far behind, to be honest. So, the issues around system strength and related matters are very much an issue of global significance, and hence CIGRE's involvement. So, as we can see, the increasing penetration of inverter-based resources is very much a global issue. And Australia is very much at the forefront of a number of those issues. So the question becomes, what is CIGRE doing to assist? Well, quite a lot is the answer. There's currently at least 20 working groups that are underway, looking at various issues associated with increasing IBR penetration. Australian representation on those working groups is very good. Two of the working groups that I'm about to talk about in a minute are actually being coordinated from Australia and have Australian conveners. And there's a number of examples already of technical brochures, which are the primary output from a CIGRE working group. There's been a number of technical brochures already published, and one of the most relevant examples is TB 671, which was titled Connection of Wind Farms to Weak AC Networks. And for those that have been involved in the system strength discussions over the last couple of years and various rule changes, some of you may recognise that title. Some of the fundamental groundwork that was used to develop the system strength assessment methodologies and the determining system strength requirements. A lot of that work actually found its origins from that particular technical brochure and the output from that working group. So CIGRE has already made a reasonably significant contribution to the Australian electricity industry through that work. In terms of how to access that sort of material, all CIGRE publications are available via eCIGRE. So this is an online portal for CIGRE members to access any amount of documentation on various topics. So what I've done on this and subsequent slides is summarised all the working groups that have terms of reference relating back to system strength or issues associated with the increasing penetration of IBR. So I won't talk about each of the working groups in detail, the intent being to just focus on one or two with direct relevance to Australia and give you a little bit of an idea of what the scope of work of the working group actually is. So in the Group A equipment category, we have Joint Working Group A1 C466, which is titled Guide on the Assessment, Specification and Design of Synchronous Condensers for Power Systems with Predominance of Low or Zero Inertia Generators. So while quite a long title, you can see the relevance of that working group to Australia, given the number of synchronous condensers that are being talked about and have already been installed, for that matter, in the NEM already. So to give you some idea of the scope of work of that working group, they're looking at the effectiveness of synchronous condensers to deliver inertia, system strength, including transient capabilities to supply short-circuit currents, and other dynamic stability contributions. They'll be looking at the physical design of new purpose-built synchronous condensers and options available depending on power system requirements, for example, adding flywheels to increase inertia, optimizing stator and excitation system designs, and optimizing reactive power capabilities. They're also going to be looking at retrofits for decommissioned and or redundant thermal generators, how they can be repurposed as synchronous condenser units, and also looking at modifications that can be undertaken to gas turbine units to allow them to operate in both generator and synchronous condenser mode of operation. So there are other aspects to the scope which I won't bother going into in detail, but hopefully that gives you a little bit of an idea as to the sorts of things that working group is looking at. So it formed in late January 2019 and is due to report back in December of 2021. In terms of the Group Bs, which are our technologies, I thought I'd mention Joint Working Group B5C461, which is titled Impact of Low Inertia Networks on Protection and Control. And the scope of that particular working group includes things like identifying, reviewing and explaining protection issues for applications in networks containing non-synchronous sources, including but not limited to distance protection polarization, distance protection dependability, frequency measurement and tracking, phase selection for single pole tripping, and impact on directional protection elements. They're also looking at ideas for controlling non-synchronous sources, especially large inverter-based sources, with the objective to maintain predictable and useful relationships between the source terminal voltage and currents to facilitate adequate performance of those protection elements that have problems today. They're also going to be making recommendations to industry regarding the feasibility of introducing different source characteristics under fault conditions to improve operation of grid protection, and also looking at various modelling issues associated with doing fault calculations. So as you can see, that's a very relevant working group for Australia, given the amount of power electronics or just IBR that's being connected in our network. And I'm sure that there'll be some very useful learnings that'll get summarised in that technical report or technical brochure. So that was commenced in August of 2018 and the final report is due in August of 2022. So still a little while off, but no doubt there'll be draft reports circulating sooner than that. So moving on to the Group C, which is our systems, there's actually quite a significant number of interesting projects, interesting working groups underway at the moment, but the two that I'd like to mention are actually being convened from Australia by the same individual, in fact, which is Babak Badzada from AEMO. Babak is convening Working Group C226, which I'll mention now. So that's titled Power System Restoration, Accounting for a Rapidly Changing Power System and Generation Mix. This is quite a significant scope of work that the group's taken on. They're going to be looking at the state of the art in terms of restoration strategies for power systems, look at an overview of worldwide restoration practices, and then begin to delve down into how to actually restart a system with the changing generation mix that we're going to have available going forward. So what are the roles of traditional synchronous generators? What are the role of inverter connected generation? What's the role of synchronous condensers in that restart process going forward? Can we use HVDC and how best to utilise HVDC as a potential restart source? The working group's also looking at the impact of DER and the issues, I suppose, associated with having DER associated with loads. So no longer do we have what you would call clean loads. In energising a feeder, it's more than likely that we're going to be energising not just a load as we've traditionally noted, being an energy-consuming device, but we're also going to be energising a certain amount of embedded generation and what that actually means for the restart sequence. So quite a significant parcel of work. I'm actually wondering whether part of the output from that technical brochure is going to be a recommendation that you only restart large power systems at night, and therefore you don't have to worry about PV. But we'll see what Babak comes up with his team. Anyway, look, that working group started in June of 2019, and it's due to report back with a technical brochure in December of 2021. So we're about 12 months away before we see the output from that particular working group. So the second working group that Babak is convening is C456, and that is electromagnetic transient simulation models for large-scale system impact studies in power systems having a high penetration of inverter connected generation. So for anyone doing connection studies in the NEM, I'm sure you'll appreciate the complexities of actually carrying out simulation studies now, and the need to not only do traditional RMS modelling in software packages like PSSE, but also now the need to undertake more detailed assessments in EMT packages such as PSCAD. So this working group is really looking at the mix of those models and investigating what is the most appropriate way to perform power system analysis. So the proposed scope of work includes things like comparison of the applicability of RMS and EMT type models for power systems having a high penetration of inverter connected generation, time domain versus frequency domain analysis methods using EMT type models, approaches for large scale network modelling in EMT type tools, including how to develop appropriate equivalent networks, techniques for improving simulation speed, correct modelling of system frequency during abnormal operating conditions, generic versus site-specific vendor models, EMT models that is, and also delves into protection system modelling, including wide area control and protection schemes. So again, quite a significant parcel of work that the group has taken on, and with absolute direct relevance to what we're doing here in Australia and within the NEM, simply just to continue connecting new generation sources. So good luck back. We wish you all the best. That particular working group is due to report back in June of 2022. So again, a little while off, but I know there's already significant progress being or progress occurring on these topics, and no doubt we'll start to see the benefits of the working group before it's actually completed officially. So as you've probably gathered, there's a relatively long gestation period on some of the technical brochures, and given the amount of detail that gets included within them, and also noting the fact that people are actually donating their time and doing that work voluntarily in addition to their normal day-to-day jobs. But never fear, there is another source of fantastic information from within CIGRE, and a good example is the papers that were published as part of the 2020 Paris E-session. We couldn't travel to Paris this year for the normal session, so it was actually moved to an online environment, and irrespective, there was still some fantastic knowledge sharing and some great information that came out of that event. So what I've done there is just listed a few that really stood out to me, and yeah, they're certainly interesting papers. They're available via CIGRE members. They're typically a 6 to 10 page report, which captures the key learnings that people have documented and shared via this format. So in summary, while Australia may be out in front, the rest of the world is certainly grappling with similar issues to us, and hence CIGRE's involvement. CIGRE members are rising to the challenges and formulating solutions which can often be replicated elsewhere, so it doesn't matter where a working group or a task force is being convened, those learnings will be readily transportable and be able to be utilised in pretty much any power system. Access to high quality material is easy once you're a member of CIGRE, so if you or your business is already a member, please utilise what is available via the various mechanisms that exist, the key one being the CIGRE website. If you're not a member, consider what you are missing out on by not being part of the conversation, and I'd really encourage you to contact CIGRE Australia for some membership information and just find out what you can gain and learn from being a member of CIGRE Australia and CIGRE more generally. So thank you for listening. I hope this presentation has been interesting, and we'll talk again soon.
Hello everyone and welcome to my presentation. My name is Abu Taleb Haddadi. I'm an engineer scientist with the Grid Operations and Planning R&D group at EPRI. In this presentation, I'll give a summary of an ongoing research work we have been doing at EPRI to study the impact of inverter-based resources on power system protection. This work has been done in collaboration with Dr. Evangelos Farantatos from EPRI and Professors Ilan Kochar and Jean Massarejan from Polytechnique Montreal. First, some background. Basically, there is a trend in the power system industry with more and more renewable energy resources such as wind and solar generators, or more generally inverter-based resources, IBRs, being connected to the power systems. The short circuit and dynamic characteristics of power systems start to change. And therefore, there is an anticipated impact on the performance of traditional protective relays, which are designed with the expectation of fault current signatures of traditional synchronous generators. This leads to a challenge for protection engineers, which need to identify such potential misoperation issues and develop solutions to prevent misoperation and ensure effective protection under high shares of IBRs. This is the objective of this study, to identify such potential protection misoperation issues and provide recommendations and guidelines to circumvent the issues and ensure effective protection with high shares of IBRs. So EPRI has been conducting research work since 2013 to study these impacts, and there is a comprehensive list of protection functions that we studied. The latest report published in 2019 presents a summary of the findings. In this presentation, I'll be focusing on power swing protection and negative sequence quantities-based protection elements and how they're impacted by IBRs. These anticipated protection challenges, they all stem off from the different fault current characteristics of IBRs compared to those of synchronous generators. So here is a key difference. Basically, for an IBR, the fault current is tightly controlled by the IBR control scheme, and therefore its characteristics is predominantly determined by the IBR control scheme, whereas for a synchronous generator, the fault current was uncontrolled and mainly defined by the electrical parameters of the source. So this control dependence of fault current of an IBR leads to the following typical characteristics. First, the fault current has a low amplitude. It has a dynamically changing phase angle, could be inductive, capacitive, or resistive depending on IBR type and control. And furthermore, they typically have no negative sequence fault current component, and they have no inherent inertia. Now, the objective here is to see how this low amplitude fault current with dynamically changing phase angle impacts the performance of traditional power system protective relays. First, we start by looking at the impact of IBRs on power swing protection. What is this protection? Basically, when there is a power swing going on, we don't want distance relays to unintentionally respond to the changes in system voltage and current and trip unfaulted lines. To prevent such a misoperation, power swing protection supervises the operation of distance relay when it detects a power swing, it blocks the operation of distance relay. How does it detect the power swing? It's by looking at the rate of change of system impedance. The idea is that this impedance moves slowly during a power swing because it is subject to system inertia. Now, with the increasing level of IBRs, system inertia declines, and therefore the impedance moves faster. Now, there is a risk of misoperation. If the impedance moves too fast, then the power swing protection may not be able to detect the swing, and as a result, the tripping of unfaulted line by distance relay may occur. To illustrate this misoperation, we consider the three levels of IBRs. One, basically no IBR, traditional power system, with 25% IBR and with 50% IBR. And we studied the response of power swing protection to these levels. And basically, we could see that increased level of IBRs leads to faster swings. Basically, the time delay that the power swing relay records becomes smaller and smaller, and at some point basically the power swing relay will not be able to detect the swing. Now the second question here is what type of IBR models? This is a question that the protection engineer needs to know what type of IBR models they should use for such studies. We consider two candidate IBR models, EMT type models, electromagnetic transient type models, which use a very detailed representation with very high resolution and accuracy in a wide range of frequencies, and stability type IBR models, which provide a quasi-steady state representation, and they capture limited dynamics in the typical range of stability studies. And we cross-examined power swing results under these two models. The objective is to see whether these two models, which use different level of modeling details, whether they can provide consistent results. And here are the comparisons. Basically, we implemented the EMT model in EMTP and a stability type model in a positive sequence software. And basically, the results were consistent to a large degree. We saw some differences at higher IBR levels. Basically, the modeling differences started to give some inconsistent results. So basically, the conclusions here is that at higher IBR levels, there is a need to improve the consistency of these models. And with regard to impact of IBRs, the conclusion was that with increased IBR levels, there is a risk of power swing protection misoperation. Next, we study the impact of IBRs on the performance of protection functions based on negative sequence quantities. These impacts, they are caused by two key differences between negative sequence fault current of an IBR and a traditional SG. Basically, the amplitude of I2 is much smaller under IBRs depending on the IBR type and control, and also the phase angle of I2 is different. Here is an example for a traditional synchronous generator and a type 4 wind turbine generator. So you can see that the amplitude is much smaller under type 4, and also the phase angle with respect to V2 is different. These two differences could lead to misoperation of overcurrent element, which uses the amplitude of I2, and the directional element, which uses the phase angle of I2. So here's an example. We consider the test system with a traditional synchronous generator and the same fault with type 4 wind turbine generator. And we saw these two misoperations. Basically, the overcurrent element did not pick up due to the low level of I2 under type 4. And the directional element also made an incorrect directionality decision due to the changed phase angle. Now, to eliminate these misoperation problems, recently, some country grid codes have revised the requirements to require inverters to provide I2 control. An example is the recent German grid code. So next we study the effectiveness of such requirements on basically the performance of protection function, whether it's possible to eliminate these misoperation issues under the German code, for example. So here are the results of the German grid code. The conclusion here was that with the adoption of German code, it is possible to eliminate some of the misoperation problems in some cases. What is this code? Basically, what does it require? It requires inverters to inject under unbalanced fault a negative sequence current whose amplitude is proportional to the negative sequence voltage at the terminal, and also it requires the negative sequence current to be predominantly reactive. So it's basically emulating the behavior of a synchronous generator. So here is the I2 behavior under type 4 with German grid code. Basically, the amplitude increases and the phase angle becomes predominantly inductive. So the increased amplitude helps resolve the misoperation of the overcurrent element, and the predominantly inductive phase angle helps resolve the misoperation of the directional element. So basically, here's a comparison under traditional control with no I2 control and I2 control based on the German code. So the misoperations, they were addressed. The next protection function is a line current differential. This function uses the current at the terminals of a protected line. By comparing these two currents, it detects a fault on the protected line. In this case, there is a risk of misoperation due to the lower fault current amplitude and dynamically changing phase angle. Basically, the wind generator may impact the current pattern on one of the terminals, and therefore LCD may encounter different current flow patterns, and it may not be able to detect a fault inside its protected zone. We consider that the traditional LCD and the alpha plane approach, which is implemented by some vendors, and basically we saw misoperations under alpha plane, and the traditional scheme remained immune. Here are the results. So under synchronous generator, basically the protection detects a fault. Under alpha planes approach, with type 4, with no IBR control, the two elements misoperated, basically the phase element and negative sequence element. But when we adopted the German grid code, the misoperation issues were fixed. And here is a response under traditional LCD. Basically, in all cases, under synchronous generator, under type 4, under German grid code, the traditional scheme was able to detect the fault. So the conclusion here is a bit counterintuitive. The traditional scheme seems to be immune, whereas the more advanced alpha plane approach shows some misoperation. So here are the conclusions. We identified risk of potential protection misoperation due to IBRs. The main causes were the lower fault current contribution by IBRs and the dynamically changing fault current phase angle, and also faster IBR controls and reduced inertia. The second conclusion is that IBR I2 control, for example, based on the German code, is a potential solution to eliminate some of these misoperation problems. However, this solution also faces its own limitation, and the final conclusion is that the full extent of the behavior of I2 control on traditional protection schemes is still unknown, and there is a need for further investigation.
Good afternoon, everyone. My name is Dr. Perez Bahrani, and I am a senior lecturer and the director of the Grid Innovation Hub at Monash University. I hope you've enjoyed the presentation so far, and in particular, Andrew's presentation on CIGRE activities on system strengths. In this presentation, I'll be talking about the examples of relevant research happening in academia, and I will walk you through a few of them which are already happening or have happened in the past. So let's start with massive integration of power electronic devices, or Project Migrate. This is a project which was funded by Horizon 2020 program in Europe, and it was concluded in 2019. It was a 4-year project with 25 partners and around 18 million euro of funding. And you can see the list of partners here as a few of the ISOs in Europe and several universities worked together over 4 years. And they were trying to answer two main questions. How much of renewables can today's electricity network cope with? And what should tomorrow's network look like to integrate more of, or even exclusively, renewables? This project, as I said, was finalized last year and concluded that with the current practice, which means having grid following inverters and traditional synchronous generators in the grid, the system can cope up to approximately 65% of IBRs. To further increase this penetration level, it was concluded that adjustment needs to be made to the control strategies of grid following inverters, and these adjustments are mainly in the form of grid forming inverters. And with these adjustments and applying grid forming technology to the grid, the penetration level can increase up to around 90% and even more than that towards 100%. You can see migrate work packages on this slide. In particular, work package number 1 and 3 are very relevant to system strengths. For more information on this exciting project, you can visit h2020-migrate.eu. Another project which started immediately after Migrate, again within Europe and within the H2020 program, is positive, or powering system flexibility in the future through renewable energy sources. This project, it's a 3-year project. The budget is around 5 million euros. And again, there are so many partners in this project, so many universities and operators in Europe. The positive project intends to support the further integration of renewable energy resources into the power system by developing the dynamic virtual power plant concept, or DVPP. This concept aims to aggregate in a portfolio some renewable resources of both dispatchable and non-dispatchable natures, thus enabling an optimal internal redispatch of resources. 2 of their objectives are very close to system strengths. 1, develop new controllers to allow renewable energy resources to contribute to ancillary services, enabling system stability ultimately. And 2, to propose new stability definitions and methodologies for stability analysis and assessment. For more information, please refer to the website positive-h2020.eu. In Australia, there is a project going on at the moment, stability enhancement of utility-scale renewable energy farms in weak grids. This is a project led by our university, Monash University, and we've got a few partners, including Australian Energy Market Operator, AEMO, AusNet Services, Hitachi ABB Power Grids, and the project is funded by the Australian Renewable Energy Agency. The project will be for 2 years, and we've just started the project this September, and we're hoping to conclude it in 2 years. You can find more information about this project in this website, which is shown on this slide. With a focus on the Australian National Electricity Market, or the NEM, this project's deliverables are mainly focused on technologies to assist the grid integration of renewable resources in weak grids. In particular, we will focus on weak grid classification, optimal sizing, allocation, and control of grid strengthening assets such as grid forming inverters and syncons, alternative control strategies for grid following inverters, and finally, the interaction of various assets in weak networks. Well, in addition to these university-led projects, Electric Power Research Institute in the US is very active in system strength related projects, and they run several research projects which are very relevant to system strength issues under the research area of transmission, operations, and planning. So if you go to their website, under their portfolio, you can find transmission operations program, transmission planning, and finally bulk system renewable and distributed energy resource integration. In particular, program 173, bulk system renewables and distributed energy resource integration program. There are 4 subcategories or sub-projects which are very relevant to system strength, and also there are some supplemental projects there that you can find and have a look at them. In particular, in this list, you can find dynamic performance for interconnection of inverter-based resources in weak grids, which is very relevant to system strengths. The Global Power System Transformation Consortium is another global program which is founded by several leading system operators, and their goal is to dramatically accelerate the transition to low emission and low cost, secure and reliable power systems. Their core team, as you can see here, consists of several leading research organizations and universities from around the globe, and its mission is to bring together key actors to support the clean energy transition via its 5 pillars. You can see their pillars here in this slide. In particular, the first one, system operator research and peer learning, has significant relevance to system strength issues. Thank you so much for your attention. My presentation has been primarily focusing on grid-connected inverters and their associated challenges in transmission networks. There are further challenges in the distribution network due to wide diversity of inverters, which will be discussed by Firuz.
Good afternoon, everyone. The topic of my presentation is challenging issues of future grids with grid-connected power electronics converters, analyzing at device and system level. I'm Firuz Zare, discipline leader of Power, Energy and Control Engineering from the School of Electrical Engineering and Information Technology at the University of Queensland. Distribution network, we have different power electronic devices that I have classified as type 1, 2, 3, and 4. But for renewable energy systems, normally we use type 3 and 4, depending on the power level and also depending on the application. So therefore, these type of converters are utilized in solar farms, rooftop solar and wind turbine, and also in battery chargers and also high quality motor drives. But because the front side is based on the LCL filter to mitigate harmonics, therefore the advantage is that they have bidirectional power flow, but some of the concerns are that they can create some resonances in terms of stability. We need to work on the control system. Type 3 and 4 are based on active front-end technology, either for single-phase or three-phase systems, and it can be utilized in different applications for wind farm, battery chargers, uninterruptible power supply, PV system, or even in motor drives when we need bidirectional power flow or we need high-quality line current for the grid-connected motor drive systems. The main point is that these systems are based on the front side filter and the back-to-back inverter. Inverter A at the grid side, inverter B at the load side, and that in fact creates bidirectional power flow, which is one of the main advantages for renewable energy systems. If you look at the control system, is very advanced when we have to measure the voltage or current for both control and synchronization. We develop the control system and we can measure the DC link voltage to generate the reference current and also to stabilize the power flow based on the either load requirement or if there is a generator to make sure that the energy transferring to the grid is accurately achieved based on the closed loop control system. So in fact, the power electronic system is based on the pulse width modulation technique, and one of the issues that we have in the grid is to make sure that we are able to control the quality based on one of the standards, either IEC or IEEE. But having said that, this type of technology, either type 3 or 4 for low or high power, is very complex in terms of control technique, PLL, switching frequency, or pulse width modulation. The filters, which is either LCL filter for grid feeding that we inject power or grid forming that we need to generate voltage across the point of common coupling, or grid impedance variation that we have no idea what's going on at the grid, whether we are talking about a weak grid or a stiff grid, and also background noise or disturbances that the system should be able to handle under normal operation. Thank you very much for your attention, and that was my presentation. Thank you.
Thank you all for joining this session. Today we would like to discuss two subjects. Firstly, we will propose a way to quantify the grid conditions based on the reactive power to voltage sensitivity. Secondly, we'll give our view on which inverter-based solution can help increase the renewable penetration in the future. When injecting power into a network as shown to the left, we have the following two stability limits. Firstly, the angle stability limit, known from synchronous machine, is the point where advancing the angle will reduce the active power in feed. This can be seen in the PQ diagram below, for where a voltage of 1 per unit, the active power can never go beyond 1.6 per unit. The voltage stability limit, which we'll mainly focus on in this presentation, occurs where increasing the voltage will reduce the reactive power flow, that is dQ dV smaller than or equal to 0. In the plot below, this is the point where the reactive power injection is higher for a voltage of 95% than for 100%. At nominal voltage and low power production, dQ dV is approximately equal to the short circuit ratio. So these two values can therefore be considered equivalent. At the nominal power for weak grids, dQ dV is considerably reduced, which means that the voltage is very sensitive to small changes in Q. This is a challenge when designing controllers. The effect of the voltage level is that increasing the sending end voltage has a positive impact on the sensitivity of at higher power flows. And vice versa. It's therefore important to control the voltage in weak grids and avoid running the production unit underexcited to avoid voltage collapses. When we have a lack of network strength, the obvious solution is to install a synchronous condenser because it adds short circuit power to the grid. So how does this affect our voltage stability limit? Here we have shown the same grid conditions as in the previous slide. And then we have added a synchronous condenser to the sending bus. For a synchronous condenser, the short-term contribution to dQ dV is the nominal power over the subtransient reactance. This particular synchronous condenser then therefore adds 1 to dQ dV, which means that the short circuit power is increased from 1.2 to 2.2. We can shift the dQ dV as much as we want upwards by installing larger synchronous condensers, but the power transfer cannot exceed the angle stability limit. So how does the value of a synchronous condenser compare to the value of real network strength? At low power, the effect of the synchronous condenser is comparable to that of a stronger grid. At high production, the short circuit power from the grid gives a higher contribution to the transfer capacity than the contribution from the synchronous condenser though. Seen from the production unit's point of view, simulating a single machine infinite bus system with an SCR of 2.2 would be too optimistic in this case. It could be an advantage to locate the synchronous condenser further into the grid in order to increase the overall stability, although this would give a lower short circuit ratio at the connection point and increase the risk of separation between the plant and the synchronous condenser in case of network outages. In some cases, some of the produced power can be consumed locally. What happens is that the local load shifts the curves to the right, which will improve the stability and increase the maximum power in feed. So seen from the production unit's point of view, simulating a single machine infinite bus system with a short circuit ratio of 1.2 would be too conservative in this case.
When looking at which solutions that the wind industry provides today, it is convenient to divide the solutions provided by the manufacturers into categories according to their grid performance features. Here the three classes proposed by ENTSO-E is used. Class 1 represents the older wind turbines with the basic functionalities. Class 2 corresponds to the level of industry standard of today, here divided into stages with basic features and more advanced features like dynamic voltage control. Class 3 describes the properties of the future wind turbine converters. The 7 features listed are those proposed by ENTSO-E to be recommended for grid forming converters for use in future grids with low short circuit ratio and high penetration of wind turbine converters. This is also divided into multiple stages. The classes of wind turbine converters is both a function of the grid strength and of the targeted grid requirements. The basic class 2 converters are limited to operate in relatively strong grids with high short circuit ratio. Dynamic voltage control and retuning of the converter control, mainly the PLL and the power controllers, provides a possibility of expanding the short circuit ratio range of the wind turbine to go below 2. To reach class 3 performance, then the wind turbine converters must be redesigned with new control algorithms and updated hardware. Here is an example of the behavior of the basic class 2 converter compared to the behavior of the advanced class 2 converter with dynamic voltage control and retuned PLL and power controllers. The simulated case is a phase-to-phase fault leading to asymmetrical voltage sag at low spark short circuit ratio at 1.5. The basic class 2 wind turbines trips due to too high low voltage on the low voltage side on the transformer. The advanced class 2 wind turbines succeeds to ride through the dip as the wind turbine is able to control the local voltage below the trip limits. The advanced class 2 converter makes use of voltage feedback both from the PPC and from the low side on the wind turbine transformer. What does it take to make wind turbines and their converters ready for future requirements for wind turbines? Some of the features for class 3 wind turbines only require updates to the control software algorithms. If the transition from class 2 to class 3 is done in stages according to the impact on the design, then there will be a market for updating existing installations and also installations currently under installation. There will be a potential to retrofit existing installations. The issues and problems would be the lengthy impact studies needed for approval of the updated controls algorithms. Newer and faster tools or processes would accelerate the time to market for these updates. Future wind turbine converters would include class 3 converters, grid forming converters. But would all future wind turbines be grid forming and full class 3 compliant? No, not all future wind turbines will be class 3. It will be a mix depending on the given grid configuration. There will also be a need for future wind turbine converters to be able to switch between class 2 grid following and class 3 grid forming according to the need. Future wind turbines will have class 3 grid forming capabilities, but this is not straightforward to reach. Design of wind turbines has been optimized over time and focus has been on maximizing the annual energy production at lowest cost. Compliant with class 3 performance will give higher mechanical loads, which will drive increased cost of the wind turbine. If a wind turbine provides inertial response, then the energy will be taken out of the rotor with reduced speed, and the wind turbine is not able to regain power at the pre-fault level before the speed is restored. In addition, the limited converter overload capability would prevent the wind turbine from providing an inertial response similar to that of a voltage source behind an impedance. To overcome this, then the converter and the turbine must be oversized compared with current design standards. The mechanical structure will have to be reinforced to cope with the increased loads. The converter must be redesigned with higher current capability by shifting to power semiconductors with higher power ratings or by adding more power semiconductors.
So to conclude, for weak grids, the behavior of the grid is highly dependent on the loading of the network. If a complete network model cannot be made available, having a plot of Q and the Q to V as a function of P would provide more information than just having the short circuit ratio and the XOR ratio. Present wind turbine converter technology is grid following with the possibility of operating close to the voltage stability limit. The future wind turbines could have grid forming capabilities with the possibility to upgrade existing solutions to comply partly with the class 3 features. This will enable operation in weak grids without synchronous machines. Thank you.